let's get going again. So before the break, we talked about basic ILS, this local search-based procedure for optimizing parameters, right? And the idea behind basic ILS was that you would do a fixed number of runs to evaluate configurations, and then basically have this local search process to perform the improvement on it. And as I've explained, coming up with the right number of runs to do is a little non-trivial, right? And if you get it wrong, as we've seen in this picture here, you can get pretty massive overfitting, meaning sort of deteriorating performance on your test set, although on your training data it's getting better and better. And that, of course, is a concern. So therefore, rather than this very basic iterated local search algorithm, what we've developed is this variant that we call focused iterated local search, focused ILS. And the main idea behind that is what we call aggressive racing, and I've briefly talked about this before when we talked about components and ingredients, but I want to make it a little bit more precise now and embed it into the context of this overall ILS procedure. So what we do is we start with basically no runs for all configurations, right? Of course, at the beginning we haven't done any runs. And then we increment the number of runs whenever the search visits a certain parameter value, right? So particularly what that means, if I get back to the same parameter configuration, I'm going to give it more runs, right? This is very much like with the job candidates. If I see the same job candidate in round 2, so to speak, I'm going to give them more problems, right? To solve more questions they have to answer in order to survive that round as well. And then there is bonus runs for configurations that win many comparisons. So there the idea is that the ones that look like they might be the very best, they get extra challenges, right, to prove themselves essentially. So there is an interesting theorem that you can prove. It's not particularly hard. It's not particularly practically useful, but it is reassuring and intellectually interesting in that it says that as the number of focused ILS search operations increases beyond any bound, we can assure that it converges in probability towards an optimal configuration, right? So that really means if you run it arbitrarily long, the probability of not finding the true optimum in this space, however large it is, vanishes, goes towards 0. The key idea in the underlying proof is that the ILS process itself actually eventually reaches any configuration. It can cover the entire space. And as the number of evaluations per configuration approaches infinity, which it will, because it will not just reach any configuration, but it will reach them over and over again, right, as you keep running, the error in the cost approximation vanishes as well. So the probability of making an incorrect assessment that this is better than that will also decrease and vanish. Good. And so here was the situation with basic ILS, and I will now show you what happens when you have focused ILS, and you can see that we really practically as well get the best of all worlds, right? We start seeing improvement around the same time that basic ILS 1, the cheapest variant here, gets improvements, but then we don't overfit, but in fact we get better and better and better, right? So you can see that this scheme really works very well. I want to point out one more thing to you, namely that this aggressive racing it's not just named aggressive racing, but it really is a racing procedure, right? It's based on this machine learning idea called racing. Okay, so speeding up RMLS further, let's talk about adaptive capping, which I also briefly mentioned before. There was this question, is a theta prime better than theta? And we basically said, well, I don't have to run it much longer than this candidate here in order to see that it's surely worse, right? I don't have to see exactly how bad it is. And so we can terminate the evaluation of configurations once they're guaranteed to be worse than the best we've seen so far, the so-called incumbent. And so then there is a theorem that says the early termination of poor configurations, if done correctly, prudently, actually does not change the trajectory of the search algorithm, but often does yield substantial speedups, especially when the best configuration is a lot faster than the worst, because then what you're kind of lopping off, what you're pruning off here, of course, can be arbitrarily large, right? Good. I briefly want to talk about a very different approach called the gender-based genetic algorithm, which actually, in our experience, doesn't perform quite as well as focused ILS in many cases, but gets close, very close in many cases, and sometimes might even be a tiny bit better. In some other cases, though, it's pretty substantially worse. So the genetic algorithm is based on this simplistic model of natural evolution, right? So we think of genes and genomes, and the genome in this case is a space of parameter configuration. So a particular instantiation, a particular genome is a parameter configuration, and then we combine the genomes of two parents to form an offspring. With that, then we can also support adaptive capping, or rather, at some degree, I'll do. So you evaluate the population members in parallel, and you can stop when the first K of them have succeeded, right? So that's the way they do it. You use n instances to evaluate configurations. You increase n in each generation, so that's their method for dealing with this problem that if you fix n and you fix it wrong, you either get overfitting or it's too slow. So they linearly increase n from n star to an end value in end. It's not recommended for small configuration budgets, and the user has to specify the number of generations ahead of time, which is not quite ideal, but it works quite well in practice. Here's another method that doubtlessly is amongst the state-of-the-art methods, so-called F-rays and iterated F-rays. Very different idea from PRMLS, which is why I want to introduce you to it. And in fact, there just has been a very new piece of work by Caceres et al. At Line 2017. So I finally got to work together with the Thomas Schütze group to integrate adaptive mapping into their IRACE procedure, which made it competitive now as well for running time optimization. So let's start with standard F-rays. The F comes from Friedman because it uses Friedman test in order to determine when configurations that are raced against each other drop out of the race, right? And so here the idea is a standard machine learning racing framework. We use the F-test to establish that some configurations are dominated. And then once we figure out that not all configurations look statistically speaking equal any longer, then we use pairwise t-tests to determine the ones that should be weeded out. That's a very standard way of doing multiple statistical tests in a racing framework like this. Now, what's more interesting is iterated F-rays. F-rays alone, for a small number of configurations can work well, but clearly you don't want to, race against each other in the first stage before you have weeded out anything. 10 to the 47 configurations, that's unthinkable. You can't possibly do this, right? If you only have 5 configurations, of course it's doable, but we typically don't. So how do you deal with large number of configurations? The way you do it is that you maintain a probability distribution over which distributions are good. So probabilistic model, this time not of the functional relationship between parameter settings and performance, but just a probabilistic model of what is a good configuration, right? And so then you sample k configurations from the distribution and you raise them, and k can be chosen small enough that that's actually feasible. You can even do that in parallel, which is quite nice. And you update the distribution from which you sample with the results of the race. Okay? There is a well-supported software package in R that doesn't have, the current version doesn't quite yet have the improvement from Line 2017 in it, but I expect that that will be released within a month or so as well. And so if you like to work in R, this is a pretty reasonable thing to use. It is about as good as PRMLS and SNAC in many cases. Sometimes one wins, sometimes the other. I would say it's a very nice piece of software to use overall. My favorite configurator, developed in my group together with Kevin Dayton-Brown and Frank Kutter over many years now, is sequential model-based algorithm configuration SNAC, which is essentially based on the sequential model-based Bayesian optimization process that I explained to you earlier, coupled with aggressive racing. That's really what SNAC is, right? And so what you do is you repeat the following steps: construct a model to predict performance, use that model to select promising configurations, compare each selected configurations against the best known, and then you basically update the model, right? So next, you don't have to typically construct the model from scratch, you can just update it, and you do that until your time budget is exhausted. Typical process. So the aggressive racing in there, how does that work? Very similar as to focus ILS, right? You do more runs for good configurations, you increase the number of runs on the incumbent, the best configuration we've seen so far, the guy who's sitting on a throne and says, I'm the king, over time. And of course, the king might change every once in a while, right? If that can compete with the next best guy, then it's going to be replaced. There is a theorem also for discrete configuration spaces as the overall time budget of SMAC is increased beyond any bound. It also converges towards optimal solutions in probability, just like focus ILS, and exactly for the same reasons. Unfortunately, that theorem does not quite hold when you use continuous parameter spaces, but in practice for continuous spaces or spaces that contain continuous parameters, it works quite well too. All right, so behind the scenes, of course, what's powering SMAC are these probabilistic models that we learn that allow us to predict performance. And we call these empirical performance models, right? So given a configuration space, which of course is a product space, containing where theta 1 is the domain of parameter 1, and so on, theta n is the domain of parameter n. For each problem instance I, you have a vector of feature value, running time data, which is essentially configuration, feature values, and performance data, like running time, and you have many of those. You want to find a mapping that predicts A's performance for a given theta and x, right? So that's the way it works. Given the instance features and given the parameter values, you want to predict the performance. There's a rich literature on such performance models, so we don't have to invent them from scratch, of course. And so in AI, these performance models have been increasingly popular because they also enable algorithm selection and many other useful things, and I will talk about selection in a bit. So there is a nice AIJ article co-written by myself, Kevin, and our former students Frank and Lynn, which, if you're interested in performance models, I would recommend to you. It's quite accessible and covers quite a bit of ground. Here in SMAC, we use typically a model that is based on random forest that seems to perform very well in general. Random forests have this advantage that they can easily deal with mixed continuous and discrete values and categorical parameters, but also with things like conditionally dependent parameters. So just to remind you, and I'm going to go through this very quickly because you can read it up in a textbook, but just to remind you, how does a regression tree work? Because a forest, of course, consists of trees, right? So how do we build a tree? Let's say we have a feature table here, parameter values, feature. We have a second feature here, maybe of the problem instance. We have a parameter here, and now we have a running time, okay? For each of those particular combinations. The feature here is a feature of the problem instance, and that captures sort of performance variability across different instances. Because remember, for the same parameter configuration, different instances can have very different performance, and we need to capture that somehow in our model as well. So what we do, we split, right? Here we split on parameter 3. We split the table into two parts, all the entries for red, right? Here, this, and all the remaining ones go over here. How do we detect such a split? There's various criteria, but typically you do it in such a way for a regression tree that the variance in these resulting tables here is minimized. Right? That's a reasonable criteria that people use, but there are alternatives to that as well. So in each internal node, you only store the split criteria that has been used, okay? And so now essentially we have the next split on feature 2 in this case. This is the continuous value, so we split on smaller or equal 3.5 and larger 3.5. So let's see, this one here would essentially go over here, and those two others would go over there. And then we can forget about that table, and so on. And then finally, in each leaf, once our tree construction process has bottomed out, we will just store the mean of the running time. So in this case, there's just 1, so it's just 3.7. In this case there, it's 2.1 plus 1.2 would be 3.3 divided by 2 is 1.65. Indeed it is, right? And here we might split a little further, right? And so that way, then we get one number in each leaf of the tree. So what do we do when we basically want to make a prediction? So let's say we have true 4.7 in red, which was not in our table. How do we use the model to predict? We just walk down the tree and return the minimum running time stored in the leaf. So what do we have? We have this red here, so we walk down here, Then we have the feature that goes 3.5, 4.7, that's greater, right? So 1.65 is what we do. And it doesn't even talk about true because this first was never used in constructing the tree, or at least not in this part of the tree, so we don't need it. So that's just it. Many ways of constructing these trees in random forest. Now I just set some regression trees. For training, we draw bootstrap samples of our data to basically simulate variability in the data. That is all to prevent overfitting, right? And then for each bootstrap sample, we fit a randomized regression tree. The way we randomize is that we restrict randomly the set of features of parameters on which gets split on each node, right? And so therefore, if we just randomly determine a subset from which we can choose, that will introduce additional variability in the tree. And that's supposed to sort of protect us from heuristically being misguided in tree construction, because tree construction typically doesn't give you a guaranteed optimal result. So then you predict with each of the trees in your forest, and you return the empirical mean and variance across the tree predictions. And that gives you a nice mean and a nice variance. Now, if you think about it very, very carefully, that variance that we estimate that way is not really a true estimator for the variance of the forest. It's a quick heuristic thing you can get. In order to get a true estimator, you would have to bootstrap over this entire thing, for example. That becomes expensive. We've tried it. It doesn't seem to be worth it. The simple heuristic seems to be working quite well in most cases. This is one of those cases where you can see that machine learning, and this is pretty standard that people do this, is a lot of tricks, essentially, in heuristics, right? Plus some nice theories, so we feel better about it. But what works well in practice often really comes down to empirical study of observation. Okay. So the complexity for n data points is pretty benign for training. It's O of t times n times log squared of n. So that's pretty good. T is the number of trees, right? So linear in the trees, and linear plus this little log factor for the data points, and the prediction, of course, is just the order of t in log n, right? Log n for providing down the tree. So this is very benign. And so you can work with even large amounts of data very well that way. We have constructed empirical performance models for hundreds and thousands of observations, and they tend to become pretty good. Good. So advantages of random forests. As I said earlier, you automatically select important input dimensions on continuous integer and categorical inputs, so it can deal with all of that. We have used that with up to 138 features, 76 parameters. We can identify important features and parameter subsets, and sometimes what you actually find is that it's just one feature and two parameters that's sufficient for getting a reasonably accurate prediction. So you don't always need all of these features, and it's quite robust. So robustness, furthermore, you don't need to typically optimize hyperparameters. You can, but it doesn't make a big difference within SNAC, with this particular use. And we already get very good predictions with few training data points. So that's what's making random forests quite attractive in our context. So, but in SNAC, there's one final thing that I want to talk about a bit regarding multiple instances, right? So how do we deal with the fact that we have multiple instances on which the performance of the algorithm might differ quite a bit? And the way we do that is we have this random forest model M that basically maps parameter values and instance features into running time predictions. So here it's instances, but in reality we look at the features, right? So now what we do is we aggregate over the instances by marginalization, right? So this is exactly what this expectation does, right? So we just basically look at the expected performance over this entire distribution of instances here. And the intuition is that we predict for each instance what it would do and then average over the predictions. That easy. And there is a more efficient implementation than doing that explicitly in random forests, which speeds up the entire procedure. Good. So let's put it all together and see how SNAC works. So we learn a random forest model from the data so far. So this gives us this model here. Then we aggregate over the instances, right, which gives us this performance estimate here. We use that model to select promising configurations, and we use that using this acquisition function here, which maximizes expected improvement, which I won't write out here, but it's a standard thing to do, expected improvement maximization. You then raise each selected configuration against the best known. Okay, so in this case, we only select one, and the best known would have been in this case here, right? So we evaluate this and raise it against this one here. see how well we do. We initialize with a single run for the default configuration. Most algorithms have some sort of a default. If not, you can just use a random one. You'll be okay. And then you basically repeat all these steps until the time budget is exhausted. And that's all there is. All right. There is a distributed version of SMAC, as I said earlier, that maintains a queue of promising configurations. So it's not just one configuration, but an entire queue. And these are raced then against the best known distributions on workload cores. So that way you can use parallel computing resources in order to accelerate this process a little bit further. Briefly about adaptive capping. Once again, we use this, of course, here. It's very important. So we have a lower bound on running time through our incumbent over here. And then we cap here, as I explained before, and that gives us a right sensor data point, right? We don't know the real value here because we basically just imported here or shortly thereafter. And so what we essentially do there is we use these right sensor data points within our expected improvement process. So here is one of them. That's a right sensor data point, right? Because at the time when we elicited this, we already had better responses. And our expected improvement criterion is adjusted to deal with that correctly. I don't want to go into the technical details so much, but there's an expectation minimization procedure that can be used in order to do this. The procedure which is quite old by now, but effective. All right, let me talk briefly about experimental evaluation. And so I want to talk to you about how well do these procedures perform, and now I've told you about a number of them, and essentially I want to give you an idea how they compare against each other on a few scenarios, right? And so what we did is we compared on 17 satisfiability and mixed integer programming configuration scenarios from a variety of applications, including verification and wildlife conservation, and I think that was a manufacturing context, using the same time budget for all the configurators, okay? And we found in the end that SMAC performed best. There were improvements in test performance of the configurations performed versus PRMLS. You know, sometimes a little worse, 0.93, often a lot better, up to 2.25. In 11 of 17 cases, significantly better. In the other cases, not significantly worse, but often insignificantly better, meaning statistically tied, right? So really, we want to do SMAC here. Versus IJCAI, this gender-based genetic algorithm, things look a little bit better yet. As you can see, 13 out of 70 cases, significantly better. But there is no silver bullet. It's not clear that you always want to use this. And we didn't include iterated F-rays here because these are all running time optimizations, and at the time, iterated F-rays didn't support capping, so it would be horrifically bad on running time optimization. This has changed as of a few months ago, but we don't have the new data for this yet. Wall clock speedups in distributed SMAC almost perfect, up to 16 parallel workers on these scenarios, and up to 50-fold with 64 workers, so that's pretty good. Pretty nice speedup. And the reductions in wall clock time that you get is from 5 hours down to 6 to 15 minutes, between 48 minutes and 2 hours. So that's a good thing to be using if you have a little cluster or a large cluster at your disposal. Very briefly, let me show you what this thing looks like, and what it looks like in practice, and what the issues that come up are when you use an algorithm configurator like SMAC. So here's the process once again. You have parameter domains and starting values. They go into the configurator. The target algorithm sits in here. Problem instances are here. And what the configurator does is it calls the target algorithm with different parameter settings runs it on different problem instances. The configurator gets returned the solution cost here, for instance, running time. And then we go around this loop merrily until we run out of time. So what does the user have to provide it here? Right? That's the first question. A parameter space declaration file. This is the example. This is an example from an actual parameter space declaration file. You can see here there's a pre-processing strategy. So the parameter is called pre-proc. It has 3 categorical values: none, simple, and expensive, and the default is simple. There's a parameter alpha that's numerical, continuous between 1 and 5, and its default is 2. And a parameter beta that lies between 0.1 and 1, and the default is 0.5. It's that simple, right? So for every parameter, you have a line like that. Then you have a wrapper for the command line call, so you don't call the target algorithm directly because you need a unified format, and often you haven't made the target algorithm, or you don't want to rewrite it to conform exactly to what the configurator, in this case SMAC, expects. So you have a little wrapper script. And so what you call here is the wrapper on instance X with a timeout of 30 seconds, pre-processing none, alpha 3, beta 0.7, and then the output of the wrapper might be something like successful after 3.4 seconds, literally. And then that's exactly what comes back here, and SMAC can understand this and then do the next call, right? So this is the call that SMAC does. This is the result that SMAC sees. Of course, you can also use the wrapper manually, like I've demonstrated here, which is great for debugging. All right, how do you run SMAC? Here's what you have to do, and all these slides, of course, are posted, so you can look at them. So you don't have to really copy anything, but of course, feel free to take pictures as well. So this is what you do. You basically, first of all, get SMAC. So this, I believe, is still the latest version. You then unpack SMAC, and you basically go into the SMAC directory. Okay? So then if you call SMAC, you get a usage screen. If you want to call SMAC for real, you give it a random seed. This is just for reproducibility of your experiments, so you want to probably give it some seed that you like. We always use 0 because it really doesn't matter. And then you give it a scenario file, which is this one here, and I'll talk about that more. The scenario file holds the location of the parameter file, the wrapper, and the problem instances. It specifies the objective function to be used, in this case minimal average running time, and the configuration budget, here 30 seconds. So this is all written in this file. And a maximum cap time per target run. So this says no target run is allowed to progress for more than 5 seconds, because it's a simple demo scenario. Okay? So then you get the output of a SMAC run. It looks like this. There is an incumbent ID, the number of runs for this incumbent. So this configuration, number 12 here, has been run 43 times on 5 instances and has actually used 42 different configurations, right? So one configuration was apparently run twice. The performance of the incumbent actually is here. So 0.012505, configuration time budget used. You can see here just 30.6 seconds. This is just 1% over. The reason for that is because we can't always terminate SMAC on the dot, so it might just go a tiny bit over rather than a tiny bit under. And then the sum of the target algorithm execution times you can see is 24.7 seconds of this. You can see most of the time actually was spent for running the target algorithm. The rest goes into constructing random forests and evaluating them and so on, right? And so then we have the CPU time of the configurator, which is of course the. So total objective of the file coming on the training set is this one here. On the test set it's here, right? So slight difference as we would expect. But generally it's quite nicely. And then we have a sample call for the final incumbent in case you ever want to run that final incumbent. And you configure it because ultimately you want a good configuration, right? So this spits out what you would have to fire up in order to actually use the optimized version of the target, right? So that's that. So you have a number of important decisions that you have to make when you use a configurator like SMAC. The first is your configuration budget. For how long do you run the configurator? This is very much akin to how long do you spend your own time as a graduate student, or if you're a professor and you prefer your graduate students to do this, how long do you tell your graduate students to spend on optimizing the algorithm, right? Very much the same thing. This is dictated by your resources and needs. So, for instance, you might want to start the configuration process before you leave work on Friday in order to then collect the result on Monday morning. If indeed you take off for the weekend and go surfing or something. Of course, the longer the better. This is an anytime algorithm. You do not get better results if you run it longer, but the returns are typically diminishing. So the typical curves really do look like this, right? They shadow out towards longer running times. A rough rule of thumb that we use is typically you want to have time for at least 1,000 target algorithm runs, right? And that establishes a relationship between the capping time for the target algorithm run and or the performance of the default, because that will typically be a good first cap, then the budget. We have achieved very good results with as few as 50 target algorithm runs as well. So if you can't afford 1,000, that's also not a showstopper. Next is the maximum cap time per target run. This is also dictated by your needs and typical instance types and so on, right? I mean, if you know that you've never seen any solver solve this instance here in less than an hour, giving a cap time of 15 minutes is not going to help, right? Because no search algorithm in the world will get any traction on this, right? So you need to be realistic there. If it's too high, you get slow progress because you have no guidance. If it's too low, you can possibly overtune to easy instances, right? Because then essentially you will be very, very much focusing on the few simple instances here that you can solve. You will focus only on these. These are all the ones that provide, the only ones that provide guidance, and therefore you won't be doing it as well. So for SAT and so on, typical competition type instances, we often use 300 CPU seconds, but it really depends on what you can reasonably do with an unconfigured version of some algorithm. Okay? So choosing the training instances. You want to have representative instances like anytime you use any type of machine learning, and you want them to be moderately hard. Why? Because if they're too hard, you won't solve many instances and you won't get much traction, right? If they're too easy, your results might not generalize. The rule of thumb that we use is mix the instance hardness, so that roughly 75% of the instances are solvable by the default of your configuration within the maximum count time. And the reason why we do this is we actually do want some instances that we can't solve yet in order to really measure progress. Because if we can start solving these, we make real progress, like big progress. Okay, so you want a sufficient number of instances. Generally, as always in machine learning, more is better, right? But the problem is if you have very homogeneous instance sets, and what I mean by homogeneous is if the algorithm behaves similarly on all of these instances, then it's just a waste of time to have huge sets of them. So sometimes 50 might be just enough. In fact, I've done configuration experiments on sets of 10 instances. I've done that configuring a solver written by Donald Knuth because Don wanted to know whether his manual efforts of optimizing his beautifully written algorithms would basically got him close to the optimum. And he wasn't so sure about this, so we decided to optimally configure that. And that's one of the last times that I personally did a lot of runs because I thought, well, Don, I'm going to be a graduate student and do this work myself. And it was very interesting because on 10 instances alone, we could configure a solver to become substantially better than any configuration you've ever seen manually before. And they were very heterogeneous instance sets. So this should all be taken with a grain of salt. Sometimes you can back out. Preferably, though, I would say it's better to have 300 or more instances, even better to have 1,000 or more instances if you can somehow generate them or make good habits of them. Okay. Decision number 2, choosing the training instances continued. So, of course, we talked about before that we have to split into training and testing instances, right? This is a very important thing because otherwise we can't sort of robustly assess our performance generalization. And so what we do is we configure on the training instances, which gives us our optimized configuration, and then we run only this one here on the test instances, which gives us an unbiased estimate of performance. So there's a big pitfall, which is to configure on your test instances. Configure on the thing that you want to be really good at. Frank writes here, this is from the dark ages. What he means is it's from prior to people having knowledge of machine learning and the horrible things that can happen when you actually peek at the test data or contaminate the test data or in any way don't have a clean test and training split, right? So we never want to do that. It's actually a fine practice and one that we recommend to do multiple configuration runs and pick the theta star, the configuration, with the best training performance, right? That's cool because we still only look at the training set. And in fact, different runs of Stack can give you very different configurations with very different performance, which is why we always do multiple runs and then actually select the one with the best training performance. But you cannot select the one with the best test performance. That would be, contaminating your training data would lead to overfitting and all the other bad things. Now, let me tell you one thing, of course. You want to win the SAT competition, for example, right? Or some other big competition. Do you really do training test split and then, pick the one that's best on training data and see how it generalizes and in the end submit this? I probably would. In the first stage, this is exactly what I would do and what you should do. But in the end, you want to train something on the best data that you have, right? Which is typically all of the data. Because the test data then become the new instances that people will throw at you at the actual event. The risk by configuring it on everything, of course, is that this might not generalize, right? However, if the configuration process generalizes nicely on some subset, the probability that if you configure it on an even bigger set, you will get something that hopelessly overfits is pretty low. So therefore, that's a reasonably safe thing to do. However, for any situation that's scientific evaluation, you can never select on the test set. This works much better on homogeneous than on heterogeneous instance sets for obvious reasons, right? Instances that have something in common, for instance, they come from the same problem domain, they're all verification instances, but not just verification instances, but verification of particular types of software or structures of circuits and so on, or use the same encoding from SAP into from something else into SAP. Then one configuration is likely to perform well on all instances, and therefore you don't need such large training sets and so on. There's a pitfall in configuring on instance sets that are too heterogeneous. Let's assume that we only have 5 instances, right, that go in our training set, and then another 3 for evaluating. That's pretty extreme, right? And the 5 are very different. So then often there is no single great overall configuration, right? And what we want to do is something a little different, namely algorithm selection, which I will talk about in 15 minutes or so. So the third decision that we have to deal with is how many parameters to expose. And the suggestion here is expose all parameters you don't know to be useless or to break severities, right? So this is PEO thinking, expose as much as you possibly can, because you can always narrow it down a little later, right? More parameters make larger gains possible, obviously, right? In a bigger space, there's potentially better solutions. But also lead to harder optimization problems. So you might run into issues that the bigger space does have better configurations, but you won't be able to find them any longer because we don't have the configuration budget. Remember these theorems that said that a configurator like Snack or Focus ILS, if you run it arbitrarily long, will actually ultimately find you with arbitrarily high probability the true optimum. But we don't know how long that takes, right? So the maximum number of parameters tackled so far was 768 in work on automatic machine learning, hyperparameter optimization. With more time, obviously, we can always search a larger space, and not all large spaces are harder to search. However, should you ever encounter a situation where you use something like Snack, and you've been very ambitious and exposed thousands of parameters, and it doesn't quite work, and you can't afford a longer configuration budget, I would recommend always an experiment with a narrow-down configuration space where you just use your human intuition, which of these parameters are actually likely the most performance critical. Make a smaller configuration spice description file, which really just means that you delete some lines from it. Run that, and typically you get better results. And then you can go into sort of an iterative procedure where after you've optimized this, you can introduce a few more parameters and optimize again, right? So use the whole thing iteratively. That often works very well. There's a pitfall here. You should never include parameters that change the problem being solved, such as the optimality threshold in mixed integer programming, right? This is the threshold that tells you how close you want to be to optimum before syntax says, yes, solve it. That's not something you can optimize, right? That's part of your problem definition. And then obviously, if you were to optimize it, Snack would say, hey, let's just have a huge gap to optimality and we can solve it much more quickly, but that's not what we want, right? So be very careful with that. Or how much memory to allow the target algorithm, right? So we'll always then want to use more and more memory. Well, in most cases, that's also not what we want. Decision number 4, how to wrap the target algorithm, right? So how do you actually have this little adapter piece that the configurator calls in order to run the target algorithm? And there are many reasons why you should always use a wrapper, because you should never trust the target algorithm. If you haven't written it, you certainly shouldn't trust it. And if you have written it, you should trust it even less, at least if you're me, because I've probably made more mistakes in programming building solvers than the average, I would think, because I tend to play and experiment a little bit more. And so, there are questions such as, will it terminate in the time that is specified? Will it correctly report its time all the time, right? Will it never use more memory than specified? Will it be correct with all the parameter settings? And typically there is uncertainty about this, at least in research applications. And so it's a good practice to wrap the target runs with a tool that controls time and memory, such as Roussel Run Solver. Very readily available tool. It does the resource control for you, and you don't have to worry. And if that one fails, then you can write email to Olivier Roussel, and he will fix it for you. But he's thought probably a lot harder than any of us want to think about resource control, and so we should just use this. And also, it's a very good practice to verify the correctness of target runs. So that means that we should detect crashes and penalize them. One of the really cool things about PPO thinking, by the way, is the following. If you're worried about your algorithm crashing in weird configurations or on weird types of instances, PPO actually helps you rather than makes this worse. How is this so? Well, if you have many different configurations and they have different errors in them, okay? So they crash on different instances. And some of them are pretty buggy and others are not, and you can't be bothered to debug, which of course is really what you should do. Then PPO, used correctly, will actually learn which of those parameter configurations are incorrect and avoid them. And you do that by penalizing crash runs, right? So you can actually learn how to avoid bad parts of the space. But that only works if you verify the correctness of target runs. And there's a pitfall if you blindly minimize target algorithm time, and this happened to many of my students when they first started working with these kind of tools. What you really do is you minimize the time to crash, right? So you have to watch out for correct output of the target algorithm. And the best ways to do it is the latter. Okay, there are further best practices and pitfalls. Pitfalls using different wrappers, comparing different configurators. That's not good. If you made a new configurator, right, and you say, hey, I'm a PPO supporter, and here's my new configurator, you should all use it. If you use different wrappers in there, your results can be tainted by it, because, for instance, your wrapper is just more or less efficient than somebody else's. So we should always use the same wrapper. And also, there can be subtle bugs that completely validate the comparison, and we've seen that actually happen in some of the comparative studies that people have done, including ourselves. Not terminating algorithm runs correctly, using a generic wrapper that handles this for you is always a good idea, and we actually provide one in Python that we use for all of our work. And if you want to work on this, I think it's also good, because then this probability of not terminating runs correctly will drastically decrease unless you are a whiz in this resource control game. There are file system issues when running many parallel experiments. We've seen it many times that when you run configuration experiments on a cluster, because they are computationally demanding, the file system can become a bottleneck. And once it does, you have all sorts of weird effects happening that taint your comparative evaluation, so you have to watch out for that. A few best practices. You should choose the configuration spaces depending on budget. If you have time for only 10 evaluations, right? If that's it, because every evaluation costs a day, it's not a good idea to have hundreds of parameters, right? I mean, you can, but it's typically not a good use of the 10 evaluations. And also, it's good to be realistic and to have reproducible running time metrics. So, for instance, CPU time is typically a good thing to look at. Wall clock time can be, of course, as we know, badly tainted by other processes running on the same cores. CPU time can be affected by this as well, actually, because the cores compete for resources, particularly in the lower levels of the memory hierarchy. And therefore, what typically works best is to count operations such as memory accesses. But that, of course, requires that you program your target algorithm, your solver, such that it does that for you. When I worked with Don Knuth, who's a firm believer that you should only ever count memory access, I learned this lesson. I said, well, Don, that's all nice in theory, but if you do this in practice, counting the memory access is so much overhead that your solver will be slowed down to the point where it's useless. And he said, well, let's just see about this. And I was amazed. I think the slowdown, at least if you program it as well as Don can, the slowdown was something like 30% or so. So it was very, very little, actually. And the correlation between CPU time measured on a highly clean environment and these mem counts was amazing. It was a straight line, so it was a perfect correlation. So these mem counts are really good. And if you want to do this, you should go and download some of Donald Knuth's software and look at it, look at how he does it, and try to do it the same way. I think it's a really cool way of doing time measurements. And then, of course, configurators should be compared on existing open source benchmarks. So there is ACLib. something that we maintain together with the group in Freiburg. And that just has a whole bunch of configuration scenarios. So if you feel you have a better configurator, the way to demonstrate this to the world is to demonstrate that it's better on AC Lit. Good. Very quickly, a few case studies so you can see some applications of algorithm configuration. So just a quick overview. It helped with numerous competitions. SAP competitions since 2009 have benefited from this. ASP competition since 2009. The International Planning Competition since 2011, Timetabling in 2007, and SMT in 2007, right? So these are all competitions that are aided by algorithm configurators, by PDO. There are other academic applications on mixed integer programming, TSP and quadratic assignment, and game theory with an interesting application to kidney exchanges. That was Thomas Santon's group at CNU. Linear algebra subroutines, improving the garbage collection in Java. That's one of my favorite applications. This is a few people at the University of Linz who basically used, unbeknownst to us, ParmILS, which at the time was the best configurator, to configure the garbage collection mechanism in Java, and got huge improvements out of this because it too has heuristic choices in it, right? Machine learning, hyperparameter optimization, and deep learning may be sort of the most important applications for you guys. And then it has been used in a lot of company settings. For instance, for the recent FCC Spectrum Auction that Kevin Leighton-Brown was involved in, a company called Auctionomics used algorithm configuration for their final mechanism that was used to allocate billions of dollars of bandwidth, of spectrum bandwidth in the US. IBM has used it for configuring Cplex. Ortec has used it in the area of analytics and optimization, Zynga for social gaming, and Acton for scaling and resource application. And what's even missing from here is a recent application by BC Hydro, the big British Columbia hydro company. They have an energy trading arm, and they actually also use automatic configuration sequence. Okay, so I want to very briefly talk about those four, just to make some selection. So this is SAT solving, back to the sphere example. So sphere, 26 parameters, just shy of 10 to the 18 configurations. We ran ParmILS 2 to 3 days on 10 machines. We had training sets. We had one training set from each of 2 distributions, and compared to the default, which was 1 week of manual tuning by the maker of sphere, by Gomerboy. And we then tested on a disjoint testing set for each distribution. And so what you see here is a little bit of a more detailed view of the numbers that I showed before. So this is the original default of sphere running time. This is the optimized version for software verification. And everything below the diagonal is a speed up. So now you can see, of course, configurators sometimes need to make trade-offs, right? The trade-off that it made here is that on instances very fast to solve, sub-seconds essentially, it actually got a little worse. But that doesn't matter because what we are optimizing here is average running time, right? And so the average gets totally dominated by the hard instance. And you can see here all these instances that the default took hours to solve up here, we can now solve it in seconds up here, right? So this is the huge improvement that you've seen. So for the easy instances, they're still kind of easy, right? Maybe a tiny bit worse. But the hard instances are orders of magnitude better. So you can see when I showed you this factor of 500, in reality it's even more impressive because it arises from drastic speed up on the very hardest instances. Okay. And then that won the quantifier free Boolean bit vector category of the SMT competition. And here is a case where we actually did hardware verification where there's less to be gained because the original version of Sphere, the default, was already quite good for it. But you see a similar picture. For the sub-second instances, we actually sacrifice some performance in order to get massive improvements up here. So look at these 2 instances here. It's actually a few order of magnitudes, and even for those ones here, we still get up to an order of magnitude improvement for the very hardest instances. So it's a little misleading to just talk about the speed up on average over all of these. It's much better to look at the harder instances because that's what we would worry about more in practice, right? Because those are the ones that we have to wait for a long time. Other examples of PDO for SAT is Satinstein, which combines ingredients from existing SAT solvers. So it's a big local search framework for SAT. It has 54 parameters over 10 to the 12 configuration, and the speed up factors we saw there were between 1.6, which would be handy winning the SAT competition on those particular instances, up to 218-fold, which is very, very significant for SAT. then Captain Jack, yet another local search framework. There we explored a completely new design space, 58 parameters over 10 to the 50 configuration, so much, much bigger than Satinstein. And after the configuration, that yielded the best known solvers at the time for 3-sat with 10K variables and a set called IL50K. So, encouraged by these results for satisfiability, we ran we designed and ran the Configurable Sat Solver Competition, or CSSC, twice in 2013 and 2014, which is how we think the competition should really be run. So in the annual SAT competition, sort of the Olympic Games for SAT solving, or Olympic Games level SAT solving, where you have, you score SAT solvers by their performance across a set of instances, and then you get medals for the best average performance with the solver default, right? And that gives misleading results, in my opinion. It's useful, it's fun, but it gives misleading results because it doesn't just evaluate the solver, it also evaluates how well the default was chosen, and that may not have too much to do with the solver. So the CSSC, what you do is you actually optimize the parameters of the solver before you evaluate, right? And that better reflects in application settings where you have homogeneous instances, so you can automatically optimize the performance, and you get medals for the best performance after the configuration process, right? So if you're a PBO believer, that's the way that competition should be run. And the solver performance improved a lot. So for instance, Sliggling is state-of-the-art solver, very prominent on circuit bus instances, which are hardware verification instances. Timeouts, which is what the SAT competition cares about most, went from 119 down to 107. So it solved 12 additional instances, which is a huge thing. The real SAT competition, the traditional one, is often one with solving one more instance than the competition, right? The next best solver. This solves 12 more. Clasp, which is a famous SAT solver, actually an ASP solver that does well on SAT as well, on an encoding of an Queen's problem, almost halves the number of timeouts here. And so here's the running time data. Again, below the diagonal are big speedups. This line is 100-fold speedup, so often between 10 and 100-fold speedup here. And PropSat, another prominent local search-based solver for randomized SAT, for random SAT instances on random 5-SAT, actually reduced the timeouts from 250 to 0. So none of these instances could be solved by PropSat before configuration, and all of them were solved within essentially 10 to 20, 30 seconds after configuration. So huge difference. So the other thing that happens is that the ranking changes, right? So the default ranking would have had SimSat first on this particular category here, then Solver 43, and after configuration, they actually land on ranks 4 and 5, whereas something that only had rank 6 in the default, actually, once you configure it, has rank 1. So what does this tell you? That tells you that if you make a new solver, right, and you compare against your competition, let's say you've made Clasp and all these other guys are already around, and you compare based on the default, you would be very discouraged to see that you're only coming in 6, right? But in the PBO world of thinking, you would optimize, of course, everyone, not just your algorithm. That would be cheating. You optimize everybody, and you see that you handily win. Because the ideas underlying Clasp are really cool. It's just that the default didn't exploit that properly for these training instances. I want to briefly talk about the FCC Spectrum Auction. Kevin David Brown gave a beautiful talk, a wider talk, I think, at IJCAI last year about this. Very nice. So the idea was that there's an increasing demand in wireless spectrum, and the US Federal Communications Commission, the FCC, has held an auction. Actually, sorry, I missed this when updating the slide. So it has held the auction last year, and the net revenue was something around $30 billion or so. So there's a key computational problem that they have to solve in this, which is feasibility testing based on interference constraints, right? If I give you a part of radio spectrum that is very close to his radio spectrum over there, and our stations are close together, we get interference, and that's not good, right? Then the communication degrades. And so essentially you can formalize this as a graph coloring problem. They had just shy of 3,000 stations, which were the nodes in the graph, and 2.7 million interference constraints, and you need to solve many different instances, because in the auction you want to decide, whom to give which parts of the spectrum. And if you solve more instances, you get higher revenue. That's the way it works, actually. Okay. And they've actually used, Kevin and his team used SNAP for this. and SAT solvers, and they improved the number of instances solved from just 73% to 99.6%, which they described in the IJCAI paper from last year. Okay, talking briefly about something different, mixed integer programming, one of the most important optimization technologies in the industry. Tons of companies and universities are using mixed solvers, mixed integer programming solvers like Cplex to solve their optimization problems. Maybe some of you have used that too, because in AI, many people, when they have a hard mixed discrete continuous optimization problem, also use Cplex for solving that. It's a commercial solver, has been developed for more than a decade. It's very powerful. Essentially solves this problem that I show up here, right? It minimizes C transpose multiplied by X such that a bunch of constraints are satisfied, and a bunch of variables here actually take integer values. If you drop this here, then you get a linear programming task which can be solved in polynomial time, right? So that it's much easier. So Cplex has been the leading solver for 15 years. There are other solvers that have performed similarly well these days, like Ruby, for example, but Cplex still is very widely used. Licensed by over 1,000 universities and 1,300 corporations. 76 performance parameters, if you're somewhat generous, meaning using a lot of them, supporting a lot of them in your configuration process, and just shy of 10 to the 50 configurations. And so here we wanted to minimize the running time for finding an optimal solution, because many users of Cplex want to run it to completion, in which case it gives you an optimal solution with a proof, with a guarantee that this actually is the optimum. So it's an exact solver. We've got speedups factored between 2 and 50, and in data work speedups up to 10,000 industry work that I mentioned previously. And again, the pattern is that on easy instances, you sometimes win, you sometimes lose. On really hard instances where the default takes hours to solve, you actually get orders of magnitude of improvement, right? So this is very typical for what we get. We also can minimize the optimality gap reached after a certain period of time. So this means, running Cplex up to some time, let's say an hour, and then you look at how close you are to optimality, and we could reduce the gap by factors of 1.3 to 8.6, which the people that we reduced the gap for were very, very happy with, because typically getting the gap even a few percent closer, smaller, is considered big progress. Cplex has a built-in tuning tool. In 2011, it was that was introduced. In 2007, that was introduced in version 11 of Cplex. After ParamLS actually already existed, it evaluates predefined good configurations and then returns the best of those. So basically, that's a bit of a racing kind of thing. And the required runtime varies from less than an hour to weeks, and you can't control it very well. Here is the default. If you use the Cplex tuning tool on a particular set of instances that was of interest here in the study, then you get a small improvement. And if you actually use ParamLS, and this is your configuration budget, then you can see at the same time where the Cplex tuning tool returns its solution, it's already much better than ParamLS. And of course, this is all test performance, and then you get better than that, right? So. And this is the worst result that I'm showing you here. The best result looks like this. The Cplex tuning tool gets nothing, and we get a 50-fold speed up on this wildlife conservation project. So quite nice. And as a result, IBM started working with us, and I think they're now working on their own configurator because they got totally convinced that PDO is the way to go and that they should really properly automatically configure it. So one of the last examples here, configuration of machine learning algorithms. Machine learning, of course, very successful, yay, all great stuff. It does require human machine learning expertise. We're so far away from saying, computer, build me a learning, build me a classifier, and it gives you a really good classifier. That's not the way machine learning works. That's why you have to take machine learning courses. And that's why companies pay a lot of money for training machine learning specialists, because you can't just have a user without much knowledge be successful in most machine learning tasks. So there is the question of how to pre-process the data, how to perform feature selection, how to select the model family, how to optimize hyperparameters, and it goes on and on and on, right? And yes, there are tools for that, but they're not trivial to use. So it all requires experience and expertise. AutoML is an approach that tries to take the human out of the loop completely. So this is really going towards computer-generated classifier for this, and then I get one of the best classifiers I can possibly imagine as a result of all of this, without having to worry about any of these things, right? So this has been very successful. At IJCAI since 2014, there has been a yearly AutoML workshop, and AutoML really is just PDO applied to machine learning. That's all it is. And I would point out that PDO was introduced as a paradigm in 2012, and AutoML was introduced in 2013 by a few groups simultaneously. Mine was one of them. We had a KDB paper that year where we essentially used the term AutoML to describe a system that automated the complete machine learning process based on Weka. So I want to talk about that briefly. AutoWeka. Weka itself is probably still the most widely used off-the-shelf machine learning package. Many of you will probably prefer scikit-learn because you like Python. But when you go out there in the wild, a lot of people use Weka, really widely used. It has over 20,000 citations on Google Scholar, that paper on Weka. And we have download data for AutoWeka, which is just one of the packages in Weka that we contributed that are amazingly high. It's a Java implementation of a broad range of methods, 27 base classifiers with up to 10 parameters each, 10 meta methods, 2 ensemble methods, 3 feature search methods, and 8 feature evaluators. So a lot of flexibility within Weka. Okay? And different methods, of course, work best on different data sets. And what we want is a true off-the-shelf solution where essentially you have kind of one button that says learn. You push the button, you go away, you come back, and you've learned a good classifier. Okay? So, talking about classification, just to keep this simple, base classifiers, we have 27 choices within Weka, each with up to 10 subparameters. If you coarsely discretize, it gets you to 10 to the 8 instantiations. There's a hierarchical structure on top of the base classifiers, right? So there is basically base classifiers and non-base classifiers. The non-base classifiers include things like ADA, boost, bagging, and so on, and other things also like voting and stacking. And then, of course, you have parameters depending on how many classes you have to learn, and so on and so forth, right? So it's a highly structured design space of classification algorithms within Weka. We didn't put it in there. That's what the Weka guys did. Feature selection, similarly, there is a search method that you have to decide which feature subsets to evaluate, an evaluation method, how to evaluate the feature subsets, and both methods have subparameters, and that gives you about 10 to the 7 instantiations. And this structure here, feature selection, you might not even want to use feature selection. You can have feature evaluation, and you can have feature search. In feature search, you can do really stepwise, in which case you have all sorts of parameters. You can do best first, in which you have all sorts of parameters and a whole bunch in between. Here you can have CFS subset, relief, and so on and so forth. All your favorite methods, right? Lots of choices. I mean, one of the reasons why machine learning has been so prolific is because lots of people got attracted to the field. Everybody made their own contribution, valid contributions, of course. But the literature is huge. There's many variants on basic machine learning algorithms that, under certain circumstances, work really well. And very few people know what to use when. And this essentially captures a whole bunch of that in terms of feature selection, and as I showed earlier about the classifiers themselves. So in total, that gives 768 parameters, 10 to the 47 configurations, similarly large as the simplex space. And it turns out that AutoWeka performs better than the best base classifier, of course, right? Even when the best base classifier is determined by an oracle. So if somebody magically tells you, here's the base classifier you should have really used, right? Even then, AutoWeka gets you something better than that because it does hyperparameter optimization, does it well. In 6 out of 20 sets, we have more than 10% reduction in relative error. So the machine learning people here will know what that means to get a 10% improvement in error. That's pretty massive. And if you compare to full grid search, which is what many people still do, here we have a union of grids over the parameters of all 27 base classifiers. AutoWeka is 100 times faster, and even though it's 100 times faster, it has better test performance in 15 out of the 21 cases. And when I say 100 times faster, it literally goes from CPU years to CPU days, right? That's what happens. AutoWeka is based on SMAC. We can also use TPE, which is the tree-based parsing estimator by Bergstra et al. Turns out and then this is more of a machine learning specific optimizer. Turns out that SMAC gets better cross-validation performance in 19 out of 21 cases, although it's not specifically made for machine learning, it's a general purpose configurator. And it also yields better test performance in 2/3 of the test cases, which is really amazing because this is a very smart machine learning algorithm, right, or hyperparameter optimization algorithm coming out of the ML community. This is a general purpose configurator that can be used for SAP, for MIP, for everything, and it still does better. The differences are usually small, but in 3 cases substantial, and in all the 3 cases, SMAC is better. So this is cool. There's a command line example here that shows you how to use AutoWeka. Okay, so it's quite simple. So you basically just call it like that, Java, and then you have the AutoWeka jar. You have these Weka classifiers, meta, and so on and so forth. Here's your training set. Here's your time limit. Here you specify that in this case.
The obvious play.
And we have a nice GUI for that, which you can download as a Weka package, and then you can just do everything in the GUI, which is really for people who don't use machine learning or Weka all the time. It's the way to go. There is a similar thing that the group of Frank has built following sort of the AutoWeka work, with which he was also involved for scikit-learn. So this also basically uses some meta-learning and ensemble building in addition. It follows an extended AutoWeka's AutoML approach and basically uses SMAC plus meta-learning to warm start the Bayesian optimization. So the idea there is you basically look at things that have worked well for other learning scenarios, like the one that you are seeing here, and you warm start the SMAC optimization process with something that worked well for that. And that could just basically jumpstart the optimization process. And it also does automatic post-hoc ensemble constructions, so when you get more than one good classifier out of the AutoML process, out of the SMAC process, you can combine them into an ensemble and you get something that's even better. Fairly nice and obvious idea. Okay, AutoScalar's configuration space, and it uses scikit-learn instead of Weka, of course, has only 15 classifiers with up to 59 hyperparameters, and here they are. I won't go through all of them, but you recognize prominent things like ADA boost, decision trees, KMN, kernel SVMs, random forests, and so on, right? And then 13 feature preprocessors with 42 hyperparameters, and again, you have a lot of things that you know: PCA, random trees embedding, kernel PCA, linear SVM preprocessing, and so on, right? Including also no preprocessing, because sometimes no preprocessing is better than using preprocessing. You won't believe it, but that actually is the case. And then there's 4 data preprocessors. There's like 1 hot encoding, imputation, balancing, and rescaling. So that leads to 110 hyperparameters, much less than the 768 in AutoWeka, but hey, you can now do it in Python. This is great. And that actually won in the 14-month AutoML challenge. Best performing approach in the auto track and human track, won both tracks in the final phases versus a team of 150 human experts. So this is one of the most impressive demonstrations that even if you think you are a really good machine learning expert, you have little chance against something like this. And it's not because people are not good at machine learning, it's because using people's time to manually select and optimize hyperparameters and so on is basically a waste. That's what we have machines for. It's trivial to use. All you do is this: import AutoScalar classification as CLS, then AutoML, you set this to CLS AutoScalar classifier, and then you AutoML fit your training data with your test, with the observations, and then you use AutoML predict in order to actually predict it on test data and you're done. Now, of course, this one here will take a while to run, right? Because it uses SMAC behind the scenes and does all this meta optimization. It's available online here if you find that interesting. Okay, very good. PDO for deep learning. Hey, everybody has to say something about deep learning, right? It would indeed be sad if PDO worked for everything but for deep learning. And of course it works for deep learning. Why shouldn't it? Because deep learning has lots of design choices, and people are not so good at making them manually. So what is deep learning? Neural networks with many layers. That's really all there is to it. Why is there so much excitement about it? Well, there has been a dramatic improvement in the state of the art in many interesting problems like speech recognition, image recognition, automatic learning of representation. So you have no more manual feature engineering, right? So it's great for these kind of things. It's truly fantastic, and there will surely be more problems on which is great as well. A whole bunch of sort of computational creativity problems. We start seeing good results too. So what changed? You know, people did neural networks with many layers in the 70s, as I said earlier. What changed? Well, we have larger data sets that helps with machine learning. We have better regularization methods like dropout, Hinton's big contribution, and we have fast GPU implementations, right? Those are essentially the three big things that change. So deep learning, however, is known to be sensitive, particularly sensitive to many design choices, right? Choice of the network architecture, the number of units per layer, kernel sizes, how many convolution layers, how many fully connected layers, and about 20 to 30 numerical choices like learning rate schedule and its parameters, momentum, batch normalization, batch size, number of epochs, dropout rates, weight, you know, goes on and on and on. So in reality, deep learning is a bag of tricks, a bag of heuristics. And that's not me saying it's not worthy. It's very, very useful, right? But it's not in any fundamental way more principled than other types of machine learning or other types of AI. It's also based on a bag of heuristic tricks, and you have to be good at these tricks to be good at deep learning. As we've already seen, PDO can help you very significantly deal with some of these design choices. And so Frank, 2 years ago, had a nice paper on this, where the application was object recognition. They parameterized the CAFE framework, used convolutional neural networks with 9 network hyperparameters, 12 hyperparameters per layer, and up to 6 layers. So a total of 81 hyperparameters. Used the CFAR10 data without data augmentation. They got the new best result for that. And SMAC actually outperformed TPE in that as well, which was the only other applicable hyperparameter optimizer for this problem. Here you can see validation error on this test set, on this set, all on test data, of course. And you can see that by configuring in both cases, you get significant improvements, but actually for SMAC, the improvements are much better by about a full percentage point. So AutoNet actually then participated in the AutoML challenge. On one data set, their data set of roughly 55,000 data points, 5,000 features and 18 classes. It basically was unstructured data, so it used a fully connected network with up to 5 layers, 14 network hyperparameters, so that was 29 hyperparameters, and they optimized for 18 hours on 5 GPUs. So that's very doable, actually, if you think about it. Okay. Result on a private test set, AUC of 90%, all other manual approaches less than 80%, and here you can actually see the score. So this is AutoNet, the PDO-based approach, and this is everybody else. So it works pretty nicely. And I think it's results like this that then induce Google to make this AutoML move, right? Because clearly there's something there, clearly it makes a lot of sense to go after it. Okay, you can get further speedups by predicting learning curves. The idea here is that humans can look inside the black box. They can predict the final performance of target algorithms once early, right? They can look at this and kind of say, yeah, this one's going well, right? This one down here is going not so well. So after a few epochs of stochastic gradient descent, you have an idea that you stop if it's not promising. Of course, you can automate this as well. We don't want it all automatic. This heuristic, they fitted linear combinations of 22 parametric models, use Monte Carlo MCMC to preserve uncertainty over the model parameters, right, market chain Monte Carlo. They stopped 4 runs early and got an overall 2-fold speedup, which is not too shabby, so it's pretty nice. You can also get speedups by reasoning over data subsets. So this addresses the problem that training is very slow for large data sets, and the solution approach there is, of course, to scale up from subsets of the given data. So you start small, and then you scale up. There is some other work from my group that does this for different problems, and it also works quite well. So for example, SVMs, the computational cost grows quadratically in data set size, so you want to be careful with using an SVM for a really massive data set, of course. But the error shrinks quite smoothly with S. And so you can actually get very nice behavior there. I don't want to go through the details here because we're a little bit low on time, but you can read this up in the 2016 archive paper that I mentioned here. So this is basically for 128th of the data set size. You see that you already get essentially the right shape of the part of the space, where in this case for these 2 parameters, you have the right values, and then yes, if you have the entire set, you get even better here, right? But you can get a lot of mileage if you have even 16 or 128 of that data set. You get into the right region. So let me actually summarize here algorithm configuration. We talked about methods, systems, practical issues, and case studies. It's an algorithm configuration is a really useful abstraction with many applications, often performs much better than human experts, and much less human expert time is required when you use it. Frank's group puts all their code there, so I encourage you to check this out. You know, you really want to think carefully about whatever the problems that you solve. If you care about performance, and I think we all do in this room, use automatic algorithm configuration to make the choices better than you can do so well manually. So with this, I want to switch to a much shorter part of the tutorial, namely portfolio-based algorithm selection. So we have about 45 minutes left. I think I want to spend about half an hour on this and talk briefly about you know, what you can do when it's not the case that one size fits all. If you can't make a configuration or one version of your algorithm that works well on everything, right? What do you do then? One thing you can do based on what I told you so far is that you just optimize separately for separate types of instances, right? But that means that you have to have access to sufficiently large training sets of these instances to make these optimized configurations. That works well, but often you can do even better. And I'll tell you a little bit how. So often no single great configuration exists. For a heterogeneous instance distribution, right, you often have it that the best overall configuration is actually not great on everything. So here's an example. 3 configurations, 1, 2, and 3, 2 types of instances mixed together, and you know, you have this kind of pattern here. You can, and this is very typical actually, it's not just a cooked example. So you typically have it that, you know, there is a trade-off to be had between solving these instances well and these instances well. And these configurations just make this trade-off differently. On average, those 3 configurations can be pretty much indistinguishable, right? So there is no single best solver. And in SAT, we've known that for a very long time, and many other problems just as well. Like in learning, like I just said, you know, there's a reason why Regression has all of these, and scikit-learn has all of these classifiers, because none of them always performs better than the others. So in SAT solving, for instance, we know that there's different solvers that win different categories of the SAT competition. And we also know that the virtual best solver, which is the best solver for individually selected for each instance, right? So if you could magically select the best of a set of solvers for every instance and call that the solver, that would be the virtual best, right? That is often much better than the single best solver, which is the solver that actually has the best aggregate performance over all the instances. There's often a huge gap. And so algorithm portfolios are an idea to basically exploit the complementary strength of different algorithms. So the first instantiation of this idea that made it prominently into the AI community was probably parallel portfolios, where you have basically one instance and a whole bunch of solvers, right? And you run them in parallel. Algorithm schedules are where you have an instance and you run it first one solver, then the second solver, then the third solver, then the fourth solver, always assuming that, you know, none of these solvers has been successful yet. And that also has been prominent for quite a while in the AI community, particularly in planning. And then there's algorithm selection, which is an old idea, goes back to John Rice in the 1970s, but only has really become prominent in the AI community, I would say around the early 2000s. And the idea here is that you have a problem instance, you extract some features, and then you have an algorithm selector that basically tells you which of these algorithms you want to run, right? And it does that based on the features. And of course, that mapping from feature values to algorithms is something you learn. So portfolios, all of these techniques have been successful in many areas. Satisfiability, here is a whole bunch of examples, all quite prominent. Constraint satisfaction as well, planning, mixed integer programming. And this is just the tip of the iceberg. There's 2 very nice surveys that show you exactly what, at least in 2008 and 2012, was the scope of these kind of portfolio-based techniques, right? And it's massive. There's so many problems for which this works well within AI and outside of AI. I want to talk about basically 2 things, one in more detail and one only very, very quickly because of time. The one I want to focus on is Satzilla, which is a framework for algorithm selection that has been particularly prominent and particularly successful in the SAP community, and then has had quite a bit of impact beyond. And that also gave rise to a paper that won the IJCAI Best Paper Award a few years ago. So the early core approach of Mozilla around 2003 and 2004, just around the time when Kevin Leighton-Brown joined UBC from Stanford. Kevin had started some of this work at Stanford and then brought it with him and got me on board with it, and that was very exciting because I had been working on certain types of SAT solvers for a long time, and it turned out that that expertise was useful in this context. But so this early work essentially was quite simple. You know, you train as part of your algorithm development a statistical model to predict the running time for each of your algorithms that you have on your menu, right? So now, if you could, of course, predict how long each of these algorithms will take for a new SAT instance, you would just pick the algorithm that's predicted to take the shortest, right? And that's exactly what you would do: predict performance for each algorithm, pick the algorithm best. And it was named after Godzilla, after a monster, primarily because the idea was that this gives rise to sort of monstrous solvers, right, with monstrous capabilities and strength, but also solvers that SAP people would look at and would go like, oh, well, you know, that's not clean and intellectually beautiful. This is sort of an ugly thing that you do on top, and yes, it might be powerful, but it's also ugly and scary, and it will never work very well. That's what they thought in the beginning. It did perform reasonably well in SAT competitions, but didn't blow anybody away. In 2003, it got 2 silver and 1 bronze, and in 2004, 2 bronze. So this is pretty nice. But as you know, when you watch the Olympics, getting bronze and silver is nice, but people really only talk about the gold medal winners, right? Those are the guys who get all the glory, and the others are just on the podium too, basically. Although it's a huge achievement in the Olympics, as it is in the SAT competition. And so we've worked more on this over the years, and I want to tell you how in the end this worked, right? But first of all, how does Mozilla really work? So you have a training set, and you have a metric that you care about, very much like an algorithm configuration, and you now have a set of candidate solvers. These can be very different solvers, or they can be different parameterizations of one solver. It doesn't matter, right? But it could be 5 different solvers from different groups that have completely different properties. And then you have the portfolio builder, this little guy here. So the training is you collect performance data for all these guys on all of the training instances, and you learn a model for selecting among the solvers. And at runtime, when you use it, right, when the portfolio builder has done its work, you evaluate the model and run the selected solver, the one that the model says it should be run. Quite simple, right? So I first want to talk about essentially how we make this portfolio-based algorithm selector at training time, right? At running time, that we have the novel instance that actually gets run by this guy and the solver gets selected. So actually, let me first talk a little bit about features, because that's important, right? If you don't have good features that allow you to build this mapping, then maybe a good mapping can't even be found. So we use over 100 features, including instance size, syntactic properties such as positive and negative clause ratio, statistics of various constraint graphs. We used Donald Knuth's clever estimate of search space size. We use tree search probing and local search probing, which just means that we run brief periods of simple tree search and local search algorithms and see how well they do. And we also look at a linear programming relaxation just for the heck of it. So now, in 2007, we extended this with even more features, and we included sort of an early algorithm schedule. So this identifies a set of what we call pre-solvers and a schedule for running them. And so then the idea is, I don't want to go into the details here too much, but the idea is that, you know, essentially computing features and then evaluating the machine learning model can be just costly enough that you're losing, you know, a lot of what you later on have to gain back in order to be competitive. So for the simplest instances, it's often good to just run something quickly and see whether it succeeds. And if that doesn't succeed, then you go through the whole algorithm selection process, right? And so that's essentially what we do with pre-solvers, and we run a few of them and we optimize offline over them. I mean, a true PBO style. We also identify a backup solver. So this is essentially the single best solver on all the remaining instances not solved by the actual pre-solvers. And that's needed in case the feature computation crashes, right? Then you want to fall back on something if you want to win the SAT competition. And By just making these adjustments in 2007 for the first time, we did win 3 gold, 1 silver, and 1 bronze. And that's when the SAP community says, oh my God, this is not just scary, but it's also really good. And they started paying very careful attention to how this works. In 2009, we improved it further. So we now basically select the best subset of component solvers to increase robustness. And for that, we basically, we did it because you want to omit weak solvers that could be accidentally selected, right? So it can always happen that you train something and have a whole bunch of solvers, but some of them get really selected and they're really kind of weak, but they do get to a small improvement. These are risky solvers, and it's sometimes better to actually kick them out. We also condition this on the choice of 3 solvers, and essentially can be done computationally efficiently because of the way it decomposes the problem. So then you keep the subset that achieves the best performance on some validation set, not test data, of course, right? We fully automated the procedure to optimize loss on the validation set. Previously, the building of the zilla, the selector, had some manual steps, but then we fully optimized it, and in 2009, we got 3 gold and 2 silver. So this is when the SAP community really went like, whoa, there must be something, because remember, you can be lucky once, right? But it's hard to be lucky twice. So that worked really well. In 2011, we did a bunch of larger contributions here, or further modifications to it, which then led to even better performance. So we basically built a classifier to determine which algorithm to use between each pair of algorithms. So for basically algorithms A and B, for every possible pair, we then train a classifier that says A better than B or not, right? And then the majority voting to basically to determine the one that we want to run. We found that that works better than just predicting running time and then selecting the one predicted to be best. And we also minimize the cost of misclassification and just using cost-sensitive variants of decision forces for vector machines. And so, essentially this has a bunch of advantages in that big and small errors are treated differently, and you can now finally use selection as a classification problem, which in some sense it really is, right? Because you really just want to classify which instances are good for which solvers, or vice versa. So we entered the 2011 SAP competition evaluation track. I'll tell you more about that later. And this is how it came out. So this is Zatzilla and Zatzilla, right? So VBS is not a real solver. That's the best that you could possibly do based on all the solvers that have been entered, right? And so VBS is sort of a theoretical upper bound on what you can do. This is the criterion that's essentially used to determine who wins. And you can see that we're quite better. The first 2 are Zatzilla variants, and they're quite a bit better than the next ones here. Okay. That was for application instances. For hard combinatorial, very similar pictures, Zatzilla, and then a whole bunch of other stuff. And a whole bunch of these others, by the way, I should say, use PBO kind of technology under the hood as well. They just don't use it the way that Zatzilla track. Actually, we did get beaten by CCA SAP. That was a new solver that, of course, we couldn't use, right? We didn't have that in our portfolio because it's never been seen before. And so this is an example where actually somebody comes up with a really clever idea that's better than sort of the cleverness extracted from all the good ideas that were there the previous year. So that was nice to see. And in the sequential portfolio track, where we were compared against techniques similar to Zatzilla that also basically try to portfolio-based solving, we also won that. So there was another solver that deserves mentioning, although it didn't rank officially. It was disqualified based on the technicality because it chose a buggy solver that returned an incorrect result. So I told you earlier about the things that can go wrong if you're not careful. Now, I'm sure these guys were not as careful as we were, but they were just unlucky in this particular case. It's not a hazard for portfolios. But its overall performance, which we asserted later on, is nearly as strong as Zatzilla. Not quite there, but it would have certainly ranked somewhere around here. 2013 onwards, algorithm selection became a victim of its own success because the SAP community essentially said, this is so good that they always win the competition, and that steals the thunder from the people who do the real work, namely develop new solvers, right? And of course, Zatzilla will never work on its own. It always needs solvers to choose from. And so they felt, and I think they were actually quite right about that if the solver developers never actually get any of the glory, they have no incentive to make better solvers, and everything will stagnate. Basically banned the portfolios from that. And so there was then an open track allowing portfolios still, and that open track was dominated by techniques like Zilla. 2014 onwards, only in submission of core solvers, and the portfolio researchers started their own competition, namely the IJCAI algorithm selection challenge, because we do need something where we can, measure the improvement of our methods, so we continue to do well on there. One very quick thing I want to mention before moving on. Of course, when you use an algorithm selector, there are many design choices you can make, right? So these are sort of now higher level design choices, because this is already a meta-algorithmic technique, something that chooses from algorithms. But the question is, how do you do it? And so we've PBO-ified that. As true PBO pioneers, we should do that, right? And so we built something that we call an autofolio, where we have a general space of algorithm selection methods, right? In this case, 54 choices, which is just, look at the overall structure of this picture here, a pretty complex interdependent structure of these parameters. And then we use algorithm configuration to select the best instantiation, right? So this is using algorithm configuration to make the best algorithm selector, right? Configuration on top of selection. Basically, then we partitioned the training benchmark instance into 10-fold, used SMAC to find the algorithm selection approach and its hyperparameters that optimize cross-validating performance, right? And so that turned out to do very well in the IJCAI Algorithm Selection Challenge 2015, which is the last one that has been run to completion. Currently, there's another one underway. We ran this. The ingredients here of an algorithm selection benchmark, of course, are a set of solvers, set of benchmark instances split into training and test, and measured performance of all solvers in all instances. So this is basically the data on which you evaluate, or on which the competition is run. And then you have 13 AS algorithm selection benchmarks from SAT, MAXSAT, CSP, answer set programming, quantified Boolean functions, and a logistics problem called container pre-marshalling. 9 competitors that use regression, classification, clustering, KNN, and so on, right? And so winning algorithms in the 3 tracks that were there was autofolio, and Zilla. So we were very happy because that was all coming out of our group. But I should say, of the other 7 entries, they also performed very strong and much better than the single solvers. So whatever you would have chosen from this in a real-world problem would have given you significant benefit. So of course, I think you should try this yourself. Zilla, you can access from there. Autofolio, you can access from there. We have features for SAT, mixed integer programming, AI planning, and TSP. If you want to use any other problems, you need to provide your own features. In many cases, making features is not so hard, actually, and you would have already, as a domain expert, some idea of what features might be actually informative. Very good. So, with that, I will switch over to the other presentation. Oops. And why is that not doing it? That is because PowerPoint is greedy and doesn't want to go away. Oh, it's gone away. So, let me actually, in the interest of time, do something here. Give me a second. So, I want to tell you something quickly and then move on to the last part of the tutorial. So obviously, Frank has a more efficient way of talking about some of these things, which is why we would have taken 10 minutes less than that, I believe. And what there is in the 10 minutes you will find on the slides offline in case you're interested, but let me just briefly explain it to you because the idea is very simple and I think you would like it and you would benefit from knowing about it. The details are not as important if you read them up in papers anyway. Put them up on the slides. So the idea is essentially the following. Algorithm selection works if you have a whole set of solvers, right? Like, the 15 solvers that have been entered into a particular category of the SAT competition last year. It can be such a set, and then you can make an algorithm selector, and maybe even make the best algorithm selector, a particularly good one, using autofolio and therefore configuration on top of selection. But what happens if you only have one solver if there's a new problem and you are the only person who's ever written the solver for it, and you strongly suspect that there isn't a single configuration of your solver that works well across the board, so plain configuration is not what you might want to do, then you can actually combine algorithm configuration and selection in another way. And that way is very interesting. And that way essentially says, let's continue to make configurations that are not just individually good for some types of instances, because you might not know for which instance you would want to use which configuration. But let's actually try to learn for which instance type you should use which configuration of the algorithm, right? You can see that this is a generalization of the algorithm configuration problem, where you're not just looking for one configuration, but for a whole set of configurations, and then you build a selector from that set of configurations that essentially uses the most appropriate setting of your parameters depending on the instance to be solved. And it turns out that that can be done. We've done it, and some other groups have done it as well. Our work is called Hydra, and the key idea is that you work in iterations where the first iteration you make an algorithm selector that is essentially, you make an algorithm configuration that's essentially good for your entire training set. In the second iteration of the procedure, you take that as given and nail it down, and now ask yourself, if I could have a second configuration and choose between the two because I'm training a selector, what should that second configuration be? This is very much like when you're building a team, right? You already have one person who's pretty great, and now the work gets more and more, so you want to hire a second person. Do you want to hire somebody just like this person one? No. You want to hire somebody who complements person one such that the performance of the team of two is maximized, right? And of course, you can use configuration to exactly optimize that objective, right? To optimize, to find person two such that person one and person two in tandem work best. To find configuration two such that a selector, like a Zapzilla selector or portfolio selector, built on configurations 1 and 2 has maximum performance. And if you can do this going from 1 to 2, you can also go doing it for a third team member, for a fourth team member, and so on. Until you get to the point where adding more team members doesn't give you an increase in performance any longer, right? And so that's what we call Hydra. It's a very interesting approach, and you find more information about it on the slides that I just skipped. For the remaining time, I want to briefly talk about software development support in further directions. And so the first thing is I want to share with you sort of a little dream I have about how in the future software development in the PBO world will look like. And you will see that this is actually quite different from the way it looks today. So in the PBO world, you might have one or more software developers that want to write a piece of software to solve a given problem. And they produce something called PBOL sources, which are PBO-enriched sources, where L is your language of choice. So I think around here probably people like Python, so let's call this PBO Python sources. Okay? So these are slightly enriched sources that can be run through a piece of software called a Weaver that extracts two things: a design space description, which remember we need in order to do configuration, and a parametric Python source. Okay? Which are exactly the two things that together with benchmark inputs, we can then feed into something like SMAC. In general, I call this a PBO design optimizer. You can think about something that, maybe looks at particular characteristics of this and this and this and chooses the most appropriate optimization algorithm here, right? SMAC or IJCAI or whatever. And then it will find instantiations of those sources, of those parameters, and therefore of the sources, that will give you an executable or something that you can package up that performs particularly well on these benchmark instances. Now what's really nice about this picture is that if somebody has a new use context, you don't need to get these guys to work again, right? But all you have to do is run the design optimizer again, and you will get something better here, right, for that use context. So that's very nice. So let me talk about design space specification. So the first, what I would recommend for you to do in the present day is just to basically use language-specific mechanisms. Just expose the parameters in any way that you know to expose them in your language, say Python or C++. So that basically means either command line parameters or conditional execution or maybe conditional compilation, right? So those are the three classical mechanisms to use for that. There is a second option, which I think ultimately in the future will be much more attractive, and that's a generic programming language extension. which will provide dedicated support for exposing parameters so that we don't have to do it manually, and specifying alternative blocks of code. The advantage of that is that it reduces the overhead for the programmer. And you know, I've watched myself and my students use PDO thinking as a design paradigm very often, even if they're already bought into the idea, the effort, and even if it's only 10 minutes to expose a new parameter is something they don't take lightly. They go like, well, I'm not sure I should really expose this, right? If we could make this a 10-second thing, it would make a big difference. Also, and more importantly, this supports a clean separation of design choices from other codes, right? And so if you think in a software engineering sort of way, design choices are really specific aspects of a piece of software, and they should be kept separate from the rest and not folded in with other conditional parts of the code. Much more importantly yet, this could provide a good basis for dedicated PDO support in software development environments like IDEs. So the key idea is to augment the sources to get PDO Java, for example, from Java plus a few selected PDO constructs, and then compile it down from, into the target language using this tool called the Weaver, right? So that's essentially the idea. Now I want to talk a little bit about this part of the process here. What do these PDO sources, what could they look like? Here's a piece of code that I've written myself about 20 years ago when I was working on my PhD thesis. And that was a solver that at the time actually worked really well, a SAT solver, and later on led to a paper that collected many, many citations. And this was the line that essentially set something called a numerator, which essentially was the numerator of a fraction that needed to be adjusted by a certain factor. And I have played around and have decided that the factor is 1.4. Based on experiments. So that's what we call a magic constant. Let's see a show of hands who believes that they never ever in their code use the magic constant. I'm just curious. Anybody who's clean? So everybody else, oh, you've never used the magic constant? Good for you, if that's the case. But everybody else has used magic constant, right? It's so tempting because you play a little bit with something and then you just leave it at the setting that worked well, right? And so here's how easy I think it should be to get rid of the magic constant. Like this, okay? Don't get hung up on the syntax, it's just one example of how it could be done. You declare a parameter, which is a float, which is called a multiplier, because this was a piece of C++ code, this makes sense, right? You give it a default of 1.4, and here's the multiplier, and bam, that's it. That's all you need to do, right? And so then these parameter declarations could appear in arbitrary places, could be right in front of it here, could be somewhere in the header file, could be at the top of the file, doesn't matter. Before or after the first use of the parameters, just to keep it simple. The access to the parameter to keep it safe is read-only, so you can, the values can only be changed and set by a command line or config file so that you can actually flatten this out, then compile it in. So it's as easy as this. So design alternatives. Here we need a different concept, the concept of a choice. That's a set of interchangeable code fragments, okay, that represent design alternatives, and these are the instances of the choice. A choice point then is a location in the program where you have such a choice. And so here's again a way of marking this up quite simply. So you could use the same kind of syntax here. So this is a choice called preprocessing. If you want to do preprocessing, there's a block of code here, and it goes up to here, right? Now, if there's two types of preprocessing, standard and enhanced, let's say you thought a little bit harder, a second occurred to you, it could be just like this, right? This is the code block for standard, this is the code block for enhanced, done. Of course, it might be that if you do pre-processing, you might also have to do some cleanup. Looks just like this, right? Again, if pre-processing is on, then you do this little code there as well. Quite simple. And you could nest it, right? So if pre-processing is on, maybe you also want to do extra processing and maybe not, right? Which you do in here. So it all works very naturally. You don't have to think about these parameters. So this Weaver then transforms the PDO code down. It is imagined to have two modes, parametric mode where it exposes parameters and makes choices accessible via conditional categorical parameters. And you can also partially instantiate where you hardwire some parameters into the code and expose others. This is great for taking some of your ideas, but also great for making the compiler do its work more effectively. Yeah, that's basically the way that something like this could work, right? And I think that would be much better. It would be a much better way to use PDO than with the existing mechanisms for holding up design alternatives. Although the existing mechanisms are also not bad at all, and you all already know how to use them. So the road ahead, I think it's very much worth working on PDOs, on better support for PDO-based software development, while people like you are already using what's currently there. So we are working on reverse for PDO, C, C++, and Java. PDO Python would be another good thing to do. So if there's anybody who feels motivated to contribute to that, that would be great. I think we need a community of people to do this. I think it would be great to have PDO-aware development platforms. Just as one example why I think that would be good. Even in the PDO world, you don't want to keep all design alternatives forever, right? So let's say you're a PDOer and there's this one choice that's pre-processing of your solver. And you've implemented 27 different pre-processing options, and you've used, as you should, the design optimizer and SMAC to optimize this for lots of things. But you need to maintain that code, right? Whenever you change the data structure, your preprocessors all have to be updated. That's a lot of work. And now we found that out of the 27, only 5 ever got selected by the optimizer. Maybe at this point, just to keep things manageable for yourself, you want to abandon a few of the others. Wouldn't it be great if your development environment would make it easy to do that? If your development environment might actually embed the PDO optimizer and then automatically and proactively tell you when you're working on that piece of the code. Only so you know, here is 15 or 16 options, design choices that have never ever been activated, right? Because they never performed well. And so that would guide you very effectively. And it would even say, would you like me to archive them for you? Not even delete them permanently, just to archive them for you and basically strip them out. And I think all of this is very, very doable. I think it would be good to have further improved and integrated PDO design optimizer. SMAC is great. Actually, Kevin Leighton-Brown and some colleagues have been working on some theoretical ideas about a new type of configurator, which I think has a lot of promise. And Frank and I have just gotten involved in trying to make this practical. So it might be that very soon we'll have something even better than SMAC. And maybe some of you will be working on design optimizers as well, which is great. I strongly believe it won't be the case that one design optimizer is best for all types of PDO scenarios. So ultimately, I imagine that the design optimizer that we want to put into a PDO-aware or PDO-supported development platform is one that selects the optimizer to be run based on characteristics of the design space. So in particular, if your design space only has 15 design choices and all of them are real valued parameters, I would make it a bet right now that you want to use not something like SMAC or GG or any of the things that I talked about, but likely something very specific for this type of situation, right? So there's more work that's needed there. And I really think we want to write debugging and performance analysis tools that support PDO sort of from the ground up. And I think that's very possible, and there's lots of exciting ideas. By the way, I should tell you one thing. I think AI is missing out in a huge way on one of the most important areas of any software design process, and that's the automation of debugging. There are a few AI researchers that work on this, but we should always keep in mind, whether we write AI software or any other type of software, I think about 70% of the development effort is testing and debugging. It would be fantastic to be really smart about that and have systems that automate this to a high degree and do a better job than people, right? Verification is one way to get completely around this, but unfortunately verification is not yet practical for everything. And meanwhile, while we still have to do testing and debugging, it would be marvelous to be a ton smarter about it. And I think PDO can help, and PDO can also benefit from more advances in that area. It's good to do more work on best practices. We have a fair bit, and I've shared what I and Frank know in this tutorial with you. There is a paper that Frank has been working on that should be coming out I think later this year on best practices on algorithm configuration. I think we'll do something similar for algorithm selection. And I'm working on a book on empirical algorithmics, which will be full of all of the sorts of advice that I think is useful in terms of best practices for algorithm selection, configuration, portfolios, and so on and so forth, right? So you will soon have sources to consult there beyond these slides. And I think there's room for many, many more applications. You've seen in the beginning a long list, right, ranging from SAP to deep learning. I would actually make you a bet, which is that for every single AI problem, which means every problem that AI researchers care about, or those want to apply AI technology, there is benefits to be reaped from using PBO. I am deeply convinced of that. We have not seen yet a single problem where we failed, where we tried to use it and it wouldn't give any performance improvements. And there's a deep reason for that, and the deep reason is, as we progress from software to intelligent software, heuristics become increasingly important, right? We said at the beginning of the tutorial, or at least I tried to convince you, that heuristics are the true thing that makes AI work and progress. There's good evidence in cognitive psychology that heuristics is what makes the human mind work as well. The defining characteristic of a heuristic is that we do not know on a principal basis when and why and how well it works. So we need to experiment. And what PBO essentially says is, in a situation like this, you should never commit to something that you don't understand in the first place and for which you don't have enough data to thoroughly evaluate it. But instead what you should do is you should consider alternatives and then optimize everything, right? Optimize over the heuristics you use essentially. I'm quite convinced this is what our human mind is doing as well, and certainly it looks very much like if you want to do AI well, that's a very effective thing. And because all AI problems depend on heuristics to solve them, I think for all AI problems, automatically selecting and configuring the heuristics will give you substantial leverage over doing it manually. And finally, I think you can gain nice scientific insights. And here, I will just want to, explain to you a little bit what I mean by that, because that's sort of a bold claim that this also leads to better science. How can this be? It is because PBO helps you to answer this question: which choices matter? And I think we all want to know the answer, because that gets us from heuristics that are really ill understood to better understood heuristics. And that is intellectually a good thing to be able to do. So some design choices clearly matter more than others, and we can see that depending on the algorithm under consideration in the given use context, and the knowledge of which of those matters can't just guide algorithm development and facilitate configuration, but also give you scientific insight. So there's three recent approaches: forward selection based on empirical performance models, which you can read about in a 2013 paper. Functional ANOVA based also on empirical performance models, which I briefly talk about, and ablation analysis, which I want to briefly talk about before closing. So functional ANOVA, the key idea is to build a regression model of algorithm performance as a function of all input parameters. I showed you earlier how we can do this, for instance, the random forest model. So this gives us an empirical performance model, and then we analyze the variance in model output, right, which means the variance in predicted performance, due to each parameter and parameter interaction, as we would typically do in ANOVA, but we do ANOVA on the functional model rather than ANOVA on the data. And that's actually all there is to it. The importance of a parameter is then the fraction of performance variation over the configuration space explained by it. And that's called the main effect in ANOVA. This is analogous for sets of parameters, in which case you get interaction effects. Okay? You do it for two parameters and you get the interaction effect between parameters 1 and 2. So just to remind you, decomposition of variance, right? For parameters P1 through Pn and a functional performance model Y, you can basically write Y in the following form, right? Y has basically a mean, which is this mu here, plus a term that depends only on one parameter, only on parameter 1, a second term that only depends on parameter 2, and so on. So those are all the main effects. And of course, if you're very lucky, this is all that you need, and you can have a perfect model. But typically you don't, because the parameter is interactive. So you need these interactive terms. This is the term that depends on parameter 1 and 2. And of course, it doesn't stop at 2 if you're not very lucky. You have to go all the way through to the full model. And so the problem is the straightforward computation of these native interaction effects actually is intractable computationally, meaning it's basically incomplete, right? Because you have to integrate over combinatorial spaces of configurations. And so for random forest models, it turns out you can actually you can get around this. There is a neat trick that I can't explain in detail here, but up to constant size interaction, you can do it exactly and efficiently in low order polynomial time, which is really cool. And so then when you study this empirically, we did it for 8 high-performance solvers for SAT, answer set programming, MIP, and TSP with 4 to 85 parameters and 12 well-known sets of benchmark data. We used random forest models for performance prediction because, as I told you, that way you can do it efficiently. We trained those on 10,000 randomly sampled configurations plus configurations from snack runs to have sort of good configurations in there as well. And so then the fraction of variance explained by main effects are C-plex on this computational sustainability domain here, 70% just on main effects. On another computational sustainability domain, 35%, that's still pretty sizable, right? So a lot just explained by single parameters. Class on software verification, almost 80%, on database query optimization, over 60%, and crypto minisat, which is a well-known SAT solver on bounded model checking and software verification in the 30% range, but still pretty nice, right? So you're getting somewhere there. And then the two interaction effects are much, much lower, as you can see here already, except for this case where they're still quite high. It's more complex. So of course this may pick up variation caused by poorly performing configurations, right? Because it's variability over the entire space that you get this, right? So there's a simple solution, which is to cap at the default performance or some quantum of the distribution of randomly sampled configurations. So you basically just, that forces you to only consider configurations that are in some sense good, and you build a model from the cap data, right? But that's sort of a happy solution. A better solution is what we call ablation analysis. That's the last thing I want to briefly talk to you about. So the key idea there is that if you have two configurations of a given algorithm, it could be the default and optimized one, A and B, you change one parameter at a time to get from A to B. And that gives you something called an ablation path, right? So one parameter at a time makes a path that eventually gets you to your configuration B. You can do that for any pair of configuration. In each step, what you do is you change the parameter to achieve the maximum gain or the minimal loss in performance. Okay, so you do that basically in a greedy fashion. And for computational efficiency, we use racing, in this case f-race, for evaluating the parameters considered in each step. So by using racing, it's basically quicker to do this exploration, which of the parameters should be modified there. Again, we did an empirical study on a very similar set of range of problems as I talked about before. In this case, we used Caramel S rather than SNAC, but it doesn't matter because they're both very good configurators, and the SNAC results are very similar anyway. And so here on LPG is an AI planner and depot planning domain. That's a very well-known planning domain from the International Planning Competition. Here is the number of parameters modified from the default, and this is the performance, in this case running time, right? So after you modify only one parameter, you already improve by more than an order of magnitude. And after that, actually, it's very little gains. So it's this one key parameter that you have to get right, which is very interesting, right? So which parameters are important? For LPG, this is the most important one, which actually makes sense because it controls a key heuristic of the solver, and then these ones here come next. Now, of course, the important parameters vary between different planning domains. So once we know this, you might think, hey, now we just have to control this one parameter and we're done. But unfortunately, that's not the case. It differs. So there's a new development which is interesting and exciting from a 2007 paper just published at IJCAI, ablation based on surrogate models, where you train an empirical performance model and then do ablation on this rather based on the real data, which saves you a lot of computation time. But ablation is a great way to find out which parameters really matter in a particular application of an algorithm to a particular use case. Okay, I will just quickly go over this here because I think that's not as interesting. Essentially, you can do a very similar analysis for algorithm selection, which also tells you which parts of an algorithm selector, which base algorithms actually work well. And you can read on this on the slides and in the accompanying papers. But it's actually not particularly different in flavor from what I've talked about to you so far. So the idea again is that essentially you try to assess, if I take out this component, how much of a difference does this make, which is very similar to the idea behind ablation, which essentially says if you take out this parameter, if you assume that it already has been set to the best value, how much more improvement can you get, right? How far does this get you? So with this, I just want to close with the take-home message here, and that is, I've told you about programming and optimization. Obviously, I'm very excited about it, but I think I've shown you that there's very good reason to be excited about it as well, because it truly can leverage computational power to construct better performing software, which is something that in AI has been driving a lot of our success, but this does this in a very principled method based on machine learning optimization. But it also enables creative thinking about design alternatives, because think about what do you do with all the time that previously you would have spent in tuning parameters. Of course, you will spend this time to think about, better ingredients that go into your framework, right? Better mechanisms that then be optimized as goals for you. And that's a great thing intellectually, I think, as well. Makes much better use of our human capabilities to come up with creative solutions. It does produce better performance and more flexible software, as I've demonstrated, and it does facilitate scientific insights into the efficacy of algorithms and their components, as I've given you a little bit of a glimpse of, and also the empirical complexity of computational problems, which we've shown in a line of work culminating in an IJCAI paper last year that essentially demonstrated that local search solvers for SAP solve phase transition problems for random tree-stack, which were thought to be sort of the prototypical hard SAP instances in cubic time, empirically, which is a pretty interesting observation, and you can show that essentially also using PDO-type techniques in order to make sure that the algorithms really show their peak performance. Overall, since I've come to think about software development in AI problem-solving approaches in the PDO way, that has very much transformed my thinking. And sort of on a semi-joking note, I should say that the citations I've accumulated to my work have probably increased tenfold since I had this revelation that I should do it this way. I won't promise that the same will work for you, and you might actually want to optimize something completely different, as do I, namely the impact on real-world applications, right? And there in particular, performance matters even more than in our competitions and our scientific papers here, and I think PDO can help you a lot with that. More information you can find here, including the tutorial slides, the full deck, on this program optimization webpage, which I plan to update soon with more material. You can read the PDO article in the Communications of the ACM, published 5 years ago, but still very much up to date in terms of the vision and why this is an exciting thing. There is a talk by Linda et al. Actually, I'm going to give this talk because Marius isn't here either, and this is joint work that we've done together on Autofolio, if you found that interesting, on Friday at 10:50 in room 203. And for those of you who might still be in Melbourne for the SAP conference next week, or CP or ICLP, they are all co-located. There is an invited talk that I will be giving there on the revolution that machine learning has caused within SAP. If you happen to go to this talk, you will recognize some of the material again, but you get a different perspective on it. There's a forthcoming book on programming optimization published by Morgan and Claypool. Frank, Kevin, and I are currently finalizing the draft for this, so this should be available within a few months. And there's also the book on empirical algorithmics that I haven't even put on here, that will appear at Oxford University, Cambridge University Press, likely later this year or early next year. Finally, if PDO works for you, make our day and let us know. We are always happy to collect success stories and give you a big shout out of the next tutorial or big talk in sort of showcasing your work and what you could make out of PDO. And share the joy and tell everybody else. If PDO doesn't work for you, don't hesitate to get in touch with us and we'll try and help you diagnose why it doesn't work. The chances are that you've just fallen into some of the pitfalls that, like any sophisticated approach are there and have to be learned to be avoided. With that, I thank you very much. I really hope that you found this enjoyable and worth your while. I'm going to be here for another few minutes for questions, but we're, just a tiny bit over the time, so I don't want to keep you all. So you can just come up and ask me questions personally. I'd be happy to take them. Or send us email, and we'll be happy to try and help you further. So happy PDOification of your own work, and keep an eye out for the rest of the conference. You will see PDO-type thinking creeping into many talks. They won't call it that, but I think it's currently spreading pretty rapidly. So if you want to be part of an exciting development, we're always looking for more people who are enthusiastic and want to help the world with lots of thinking about building software. Thank you very much.